Stefano Sarao Manelli, who's now at Chalmers, and he'll tell us about dynamics of bias in SGD training. Stefano, take it away.
Thank you. Okay, it's very nice to be here. And I'm going to talk about something that is slightly different. I will focus on a particular application of machine learning, which is the problem of fairness. I will start with some introduction before digging into the core of the problem. And this is just about motivating why fairness is important in a machine learning setting. I was kind of surprised when I learned how old the problem is. So this is the first confirmed case of machine learning discrimination. This happened in London School, St. George Hospital Medical School in London, where at the time of the event, 2,500 applicants were applying every year. And about 25% of them were admitted to the second stage of the interview process, and then about 70% were getting the offer. So in 1982, the Vice Dean proposed to automatize the process, and there was something quite fancy known as machine learning happening at the time, so they decided to try it out. And they trained an algorithm which performed quite well on the previous data. But unfortunately, as you can imagine, because this is in my presentation on machine learning discrimination, in a few years there was a surprising lack of diversity in the applicants in terms of gender and race. And indeed, it was shown that the algorithm was attributing large importance of attributes like place of birth or the name, and therefore was kind of perpetuating biases already present in the data set. But this is not the end of the story for what concerns me, because I think there is a strong, let's say, bias in our field to believe that the problem lies in the data set, and instead this is not enough to explain the entire picture. I like to take this example because it's particularly visual. So here, what you see is the results of some query in Google Images. So in this case, you can see the results from the word CEO. And then what they did was just look at the first one of the images, count the number of men and the number of women, and then use this, compare this number with the percentage from the National Bureau of Statistics in the US. And so here there are a couple of examples. You can see CEO, you can see developer. You can see that the actual number is much larger than the number reported by Google search. And if you generalize this to a larger number of jobs, you can see this kind of pattern. So you can see here on the vertical axis the result of Google Images, on the vertical axis Google Images, horizontal axis the actual statistics. And what you can see here is that the algorithm tends to underestimate the number of women when you are less than 50% of people in the position, in that job, and overestimate when you have more than that. And so it is not just reproducing the bias that is in the data set, but it is amplifying the bias. So in general, I think we should move away from considering the machine learning discrimination problem, machine learning inference problem as a problem of data, but consider that we have actually a quite complex pipeline when we design a machine learning system. And so other aspects can contribute into injecting bias into our system. And so this is not only me saying that. In the recent years, there have been a series of results on this. So we have some results on overparameterization that can increase bias, results on data structure, which is going to be basically the topic of the next slides, and architecture complexity, pruning, even the batch randomness and the activation function that you choose can introduce some bias in the system. So I think that as theoreticians, this is a very interesting problem, and there is lots that we don't understand yet. I decided to start looking into it, And I'm doing this in the approach of a physicist, which is an approach that is based on modeling. So we have seen some models here in the previous talks. One that is very common is the teacher-student model. So just a very brief recap, you have a Gaussian cloud or whatever statistics, whatever distribution you may like. And then you just sample an hypervector, a vector that generates an hyperplane. This separates the positive label from the negative label, and this creates a binary classification task. Another very common model is the Gaussian mixer model, which in this case you have different Gaussians with respect to the previous model where you often have central data. Here you have some mean, and in this case you have possibly overlapping Gaussians, and you want to distinguish which, from which Gaussian each point came from. So in our approach, since we wanted to model both belonging to a group and a classification task, we combine these two. So we use a Gaussian mixture to create the structure for the groups. So being part of a Gaussian means that you are part of a group. But then we sample hyperplanes for generating labels. And now you can see that we have different hyperplanes here because we assume that possibly you can have two different teacher vectors. And so now if you play with the angle between the vectors, you can play with how similar are the learning rules. So the correlation between input-output mapping of the two groups. And then the model works as usual. You first assign a group to the sample. So in this case, we assume that you have a probability rho of sampling from one group and 1 minus rho of sampling from the other group. Of course, rho is between 0 and 1. Then you generate a sample. For this, you need to sample first the separation between the classes, so a shift vector. And then you randomly generate the sample using a Gaussian. And finally, you generate the label. And for this, you need the teacher, which in our case will be lying on a n-dimensional sphere. And you can play with all these parameters. So you can play with how the teacher is aligned with the shift, how much the teachers are aligned one with another, et cetera, et cetera. At the end of the day, you will have quite a lot of parameters, but we won't explore all of them because that will be very boring. But we will consider some case studies that I think are interesting. And the reason why we choose this model is because it is analytically tractable. Indeed, in 9 dimensions, you can define a set of sufficient statistics or order parameters, which are just the overlaps of all these vectors that I mentioned so far. So you have the self-overlap of the student classifier, which is itself a single layer neural network, the overlap of the student with the shift vector, the overlap of the two teachers, et cetera, et cetera. Okay, so this is a quite standard setting. I don't think I'm saying anything too new, but this is the kind of framework we are working with. And so before going into the newest result, something that we managed to show in this model is that, well, first of all, if you have a mismatch model, so you have two hyperplanes that are generating the labels, well, you can create some strong bias. So in this case, what you see on the horizontal axis is the relative representation, and on the vertical axis, the two accuracy condition to the two groups. You can see that if you have a very high unbalance, so one group is way more present than the other, you can have a very strong bias, a large difference in accuracy. But as you increase but even if you consider a matched model, you can have strong bias. So in this case, you can see again that there is a big gap between the two accuracies. You can push the picture further and see what happens if you have a matched model and you have equal accuracy, equal relative representation, so a balanced data set. But as you play with the variance of the two clusters, you can create some strong imbalance. And here what I'm showing is, with this color, the ratio between the accuracies. And I put the ratio in such a way that it's always between 0 and 1. So when you see a dark color, this means that you have a strong bias. So in this case, what you are seeing here is that if you have large accuracy, then it's kind of harder to classify the groups. And therefore, you will need more samples. And so having a balanced data set will not guarantee that you have a fair classification. So all of these, it's kind of straightforward when you think a bit deeper about that. But in general, many practitioners just try to balance the data set, which is not the right thing to do in some cases. And so the last point that I want to convey about this previous study is that you may be tempted, of course, if you have the group labels, to split the data set and say, OK, let me train a classifier on the first group and a classifier on the second group. But there is some positive transfer that is important here. If you have enough rule similarity and you don't have enough data, then it's still convenient to train jointly, even though this will create some discrimination. So it is not always the case, but often it's still better to use the entire data set rather than splitting. But today, what I'm going to talk about is actually another problem, still related to this model that I introduced, which is the one of how bias changes throughout training. This goes to an assumption that is quite common, and also in our experience, I think we have seen this kind of plot often. So when you train on a data set, if you condition accuracy of the different classes or groups, you may see something like this. So in this case, it's an example for an unbalanced data set. So in this case, you have way more elements from class 1 rather than class 0. And you can see that the accuracy condition to the class is very rapidly going high up for the class 1, and is way slower to get up for class 0. Now, an assumption that we may make is that, well, the assumption that we can make is this bias is consistent throughout learning. And I can use this assumption to create some algorithm that will use the information about the first epochs of training to estimate the bias in the two groups. And then I can reweight the groups and then train again. And this is something that can improve or can mitigate the bias a bit. But then the question is this assumption correct? Because, well, we don't know. It is just an empirical observation. So what we did was to revisit an experiment done by Bell and Segun in 2022 for understanding this bias in machine learning systems. So the experiment is the following. I am training a neural network, in this case a two-layer neural network, on CFAR. And in this case, I will split the classes of CFAR into two groups. So the first group will be deer, bird, frog, and horse. And the second group will be car, airplane, automobile, and truck. And so now you can also see that I assign different colors. So deer, frog, car, and automobile are in red because they correspond to the -1 label. So this is a way to create some classification problem and then create some groups within the classification problem. And then I can condition on different groups to see how it is the performance affected. And so I will take 90% from group 1 and 10% from group 2, and I create this mixture and I train jointly. OK, after all of this, what we see is something like the following. So you can see that the accuracy at the beginning improves rapidly for group, the red group, which in this case is group 2. And then will improve rapidly for group 1. So there is a crossing in the accuracy, which is way different from what we have seen in the other example and what this assumption is about. So the rest of the talk is going to explain why this is happening and when this can occur. The spoiler is that I didn't choose these groups randomly. There is a criterion for that, but in order to understand what is the criterion, we have to dig a bit more into the analysis. Okay, so now I'm taking back the model that I introduced previously. Let's keep in mind the order parameters or sufficient statistics for this problem, these overlaps. And now I will consider an analysis that has been pioneered by Sad and Sola, Biel and Schwartz, but then there have been several extensions. Sebastian is one of among the people that contributed most to this. And it's a simple analysis to, in the main field regime, to study all-line stochastic in descent. And so each time you receive a new sample, there is no correlation between the samples, and then you cannot revisit it. And the key output of this analysis is that you can characterize the evolution of the system using a set of ordinary differential equations for the order parameters. So this is just one example of one of the nicest of these equations, but it is just to show you how they look like. Of course, there is some additional work to be done in order to make it usable, but this is more or less what this is about. And then I will make another, and this is quite strong assumption. I will assume that my classifier is a linear classifier. In this case, I not only get an ordinary differential equation, but I have an explicit solution for this ordinary differential equation. This solution looks like this. So this is the equation of the dynamics for all the order parameters. I'm not asking you to read this equation. What I want you to see here is that this is the sum of some exponentials. And now, if I focus on this exponential, I can understand what are the leading time scales for this problem. So if you look at all the exponents, you will realize there are 3 time scales that are relevant. And the rest of the analysis, the rest of the slides for this part will be understanding how these time scales contribute to my problem. So I will take some simplified versions of the model to understand this. So the first case will combine the exponent for R and the exponent for M, so the teacher-student overlap and the student-shift vector overlap. This is a case that corresponds to spurious correlations. So in this case, what you have is quite very common. If you have a data set of land birds and seabirds, there is a strong correlation between the landscape of the image and which kind of bird you see. And so algorithms tend to be very confused when they see a duck that is not on the water. So we can model this within our framework, and this is basically something very similar to what Sagawa did, but just rephrased in our model. In this case, you take a single teacher, so the overlap between the teacher vector is 1. But you create a strong correlation between group membership and the teacher. So what you can see here is that basically you have, if you infer correctly the shift vector, you have already a very high accuracy. Of course, you will make some mistakes in this region here on the border of the Gaussians, but otherwise you will have quite a decent accuracy. And indeed, this is, if you have a very far apart clusters, this is what the algorithm tends to learn first, because this is quite salient. And indeed, you can see that at the beginning in the loss, you are going down quite fast, and you plateau for a while, and then you go down again. And you can understand this in terms of the overlaps within the teacher and the shift vector, the student and the shift vector, which is given in green here. This is the cosine similarity. And then from the student and the teacher vector. And so you can see that the time scale for learning 1 is faster than time scale for learning the second. And this is exactly what these 2 time scales are about. Okay, so what this result is telling us is that there are spurious correlations are often learned faster, but they can asymptotically disappear. And of course, this is a strong claim that is, I think, is related to the fact that we are in online learning setting, and so it's hard to get stuck in a local minimum. The second case that I want to show is when I combine the time scale for the teacher-student overlap and the student-student overlap. In this case, to get rid of the other time scale, I'm considering an hopeless situation where I center two clusters, one into the other, and then I assign two different decision boundaries. So the student is forced to either align with one teacher or the other or somewhere in between. So there is no way for the student to solve the task. So if you play around with the setting of the problem, now you can see the crossing phenomenon that we have observed before. So you can see here that I have the performance of the two groups, while the average performance, the weighted average performance is going down steadily. For the condition performance, I see some crossing happening, so some non-monotonic behavior. And so this is the emergence of the bias crossing phenomenon, and we can understand what is going on by looking at theory. So if I look at the equations, I can first focus on the initial dynamics and see which class is advantaged first, which group is advantaged first. So I can just perturb the increment of the loss, so how fast I'm learning one group with respect to the other. This gives me this very simple equation. And if I compare the one group with the other, I will get this expression. And so what you can see is that you have something that depends on the ratio of the two variances under the square root. And so if I increase the variance of group plus, for instance, I can speed up learning that group against the other. Now, if I want to see what happens at the end of the learning instead, I can focus on the asymptotic term in the teacher-student overlap. And I can see that this is something that depends on the relative representation. So how likely am I to sample from group plus or from group minus? So if I combine these two results together, I can see that at the beginning of the dynamics, there is going to be saliency that dominates, so the variance or the brightness of your images. And at the end of the training, instead, relative representation will play an important role. So now I can combine all these results together and try to understand what is going on. And if I play with my parameters, I can get situations that are quite funny looking, like the one that you can see here, where at the beginning of my training, the group minus will be at disadvantage, then it will be advantaged in the middle part of the dynamics, and then will be disadvantaged again. And this comes only from our understanding of what is going on in this system. So at the beginning, what is relevant is the spurious correlation. So if I have clusters that are very dense, so small variance, and they have coherent information, for instance, we have mostly positive labels or mostly negative labels, then this is going to attract my dynamic the most. In the red phase, instead, it's going to be just variance to dominate. So if I have high saliency, high brightness, high variance, this will attract my dynamics. And finally, in the last phase of learning, I will see the relative representation to be important. So if I play with this parameter enough, I can have a situation like this. But of course, in reality, you cannot play with the parameters, but you have to accept the data set you have. But now you can kind of understand what are the issues that you may encounter depending on the kind of data set you have. So now this is, of course, a result that is derived for a single layer linear network. So we must test if this has some application to deeper and more complex settings. So we run a couple of experiments. First is the one that I mentioned at the beginning, this Bell and Segun one, where we obtain this plot that I showed before. And now I can explain how I obtain the groups. So what I did here was just I sorted all the groups, all the classes according to how bright the images were. And then I just take the most bright ones and I put them in group 2, and I take the least bright one and I put them in group 1. And this is all the trick that I've done to create this data set. Then what I had to do next was just mixing them together, and indeed you can see the emergence of the crossing. And now if I move from rho equal to 0.9 in this case, I can see what is going on. So you can see here that the crossing is disappearing, and eventually you have just a monotonic descent of both curves, so there is no bias crossing anymore. But another thing that is interesting that you can observe from this image, and this is coherent with our theory, is that relative representation enters only at the end of the dynamics. At the beginning, it's not as relevant. And indeed, you can see that there is very little change in the first part of the curve, but at the end, the final part is instead changed quite a lot. Okay, then we did other experiments. We did the MNIST because all theoreticians like MNIST. So in this case, we took digits from 0 to 4 and from 5 to 9, and we applied some rotations. So now the angle of rotation is basically our teacher, and I can create more and less similar teachers. With this, I can, again, obtain the bias crossing phenomenon, and I can also obtain the double crossing phenomenon that I showed in the theoretical setting. But now I want to test another prediction that we had, so the importance of variance. And to do that, I will just increase the value of the images of these MNIST digits. So I will just multiply them for a constant factor. So if I do that, and I do this for the group minus, which is the red one, you can see that basically I can accelerate the dynamics for that group. There is a little second order effect that our theory is not able to account in group 1, but you can see that basically nothing changes, or very little is changing except for the first phase of the dynamics, which is affecting group 2. Okay. Then we took another experiment, and in this case, we are considering the CELEB data set. In this case, we are training, I think, a ResNet 18 or some ResNet. We didn't want to make any manipulation. We wanted to show that this phenomenon can actually emerge naturally without mixing the groups or without any weird rotation. And so we just took a series of attributes. We assigned them to the target, so to the label, and a series of attributes that we assigned them to the group. And then you can see that even in this case where with no manipulation, you can see the emergence of bias crossing. So again, here, what I'm showing is the accuracy in the top plot. I'm showing the accuracy for group plus and group minus. And you can see that there is this crossing behavior. And in the second row, I'm highlighting this by taking the difference between the two accuracies. And you can see that, yeah, you have exactly the crossing. So, of course, this doesn't happen for all the attributes. What we did was just randomly selecting a bunch of them and see which one was showing the phenomenon. But the fact that this can occur in a natural setting without any change should be at least concerning for applications. And this is basically all I wanted to say. In conclusion, what I told you was that several aspects of the machine learning pipeline can potentially generate an amplified bias. Many of these aspects are underexplored, and there are some assumptions that we make under the method that we use in practice that do not have some solid theoretical foundation. So this is room for us to work on. Then I focus on two aspects. I focus on data structure, and then I focus on the SGD learning dynamics, and I show that there is something to be learned there, even in single-layer perceptrons, in single-layer neural networks. And then I show that our result can show that the dynamics can be non-monotonic, and that there are specific features of the data statistics that characterize the dynamics at different stages of learning. There are several open questions that I hope to answer in the next year, or somebody else will answer this for me. We have a very simple model with no memorization because we are in the line setting, so I think this is a strong limitation of our model. At the moment, we are not considering multi-class, which is, and there is some interaction between classes, so this is something also that we should take into account. We are not considering the impact of prior knowledge, so initialization mostly. And so this is something that I wish to do next. And that is all. I should thank all my collaborators. In particular, Aristide, Anchit, and Rosine were the ones that contributed to this paper, but also Federica, Negar, and Luca contributed to the framework that we are using here. Yeah, and thank you.
We have time for some questions.
Thank you for the very nice talk. What happens if I set up this 90%, 10% setting, and I would just scale the data, keep the ratio, but make the data larger? Does the effect vanish?
No, it doesn't vanish, but you get something different. So it is not just about scaling. Now, what can happen? So, I'm not sure what it can happen, but you have to be a bit careful when you do this kind of manipulation, because in practice what you're doing is just it's equivalent to do loss reweighting in practice for this model, because everything is linear. And when you do loss reweighting, actually you don't get perfect accuracy again. So we must be a bit careful. At the moment, I cannot tell you what I think should happen, though.
Okay. Can you go back to this experiment you showed when you were changing the class imbalance and you were showing that it affected actually the later part of the training/learning curves? I was a bit puzzled by this, right? Because, so how does it, there's also this other limit, right? In which connects to the things we heard in the previous two talks, right? That is, I can think of class imbalance and some really zero-order information, like the sort of zero-order polynomial component of the task. And so from those kind of analysis, I would always expect it to learn it first.
So I think the role of relative representation is happening also before, but now you have to compare this with the strength of the gradient. With the strength of the gradient. So basically this is always multiplying your gradient for both classes. So the point is that the gradient can be much, much stronger than in order one factor. And this is indeed what is happening here. So if you have a variance that is 10 times more, even if you are moving from 0.5 to 0.7 class imbalance, then you get a much stronger impact from the gradient itself.
So, yeah, we can basically say that this tells us something really about the variance as opposed to class separation. The fact that it modifies the latter part as opposed to the former, no?
Yeah, I think you can say that.
I'll ask one. Can you comment on the degree of universality that you expect for your theory predictions? Do you think that you could get precise learning curves, for example, for the experiments that you show on Celebay and the other data sets that you have?
No, well, that would be a bit far. I would be happy to get something analogous to linear networks already. I think in general I see that this is quite robust, but all of this is just a first order effect. So In the case of CellAD, you have so many other terms that are contributing. For instance, here we are limited to the first two moments of the data distribution. And we know that higher order moments are extremely relevant, but I don't know how to account for them. I think they play a role, but from what I've seen is something that is happening later on. And indeed, one of the main problems that we have when you actually deal with the real case scenario is that these time scales are very much, they are very close one with another. So then the second order effect becomes very relevant because this can really move them, separate the two, or the three. So yeah, I think for online learning in a simple setting, teacher, student, even two-layer, etc., I think this should be rather robust. When you get very complex data structure, then I think something can break. I hope it won't break the first order, but I cannot be entirely sure.
Thank you. One more.
Thank you for the talk. I want to ask, what about when we have imbalances on the levels? Like in the case we have some kind of level noise on the data set.
Yes. We didn't study this in particular. Yeah, we didn't study this in particular. Do you have any question more specific? I think there should be something similar happening, but maybe if you have something more specific in mind, we can discuss it. Okay. Yeah, then I don't know, but I'm happy to chat with you if you have some idea of where we can go. Yeah, definitely the model can account for that. But again, there are a lot of parameters here, so we explore just a subset of those.
All right. Any other questions? Then if not, this is a good moment to break for lunch, and let's thank all the speakers of the morning again.